Welcome back. So today what we are going to talk about is classical probability density. Now we have had a very brief outline of probability theory, and we basically reviewed the points we required, the things we required to develop statistical mechanics. So continuing on the same lines, we want to look at classical probability density. So typically we want to describe a system, a physical system with a large degree of freedom. Right? For example, this can be a hydrostatic system with n particles which are contained in a box. Right? Now these n particles can be interacting as well as or can be non-interacting. Right? But essentially the dynamics is governed by the Hamiltonian dynamics. So you have the Newton's equation of motion, and the particles' trajectories are updated based on this Newton's equation of motion. So before even we want to look at this n particle system, let's look at a very simple system where I have a single particle, and when I have a single particle, interaction doesn't come into the picture, and this particle is contained within a box of length L. Right? Now clearly, if I now ask you the question that what is the probability of finding the particle between x and x plus dx, the answer is, since the particle doesn't have any interaction present, that probability is 1 by L dx. So that you can immediately read off that the probability density is given by 1 by L. If I now put in, so I have one particle over here, then I put in another particle over here. Each of these particles has a size of, let's say, A. Then my for two particle system, this quantity becomes 1 by L minus A. In the former picture, when I had only one single particle, of course, talking about probability is meaningless in the sense that I can solve Newton's equation of motion. I know that the trajectory is x equal to v naught t, right? So I can find out where the particle is at exactly the same time. But now when you go to a two-particle system, see, this question becomes slightly more difficult to answer. It's non-trivial to answer. And then I can go to a three-particle system. Right? I can go to a three-particle system where my probability density is going to be L minus A, L minus 2A. And this question becomes even more complicated, that if I want to know what is the probability of finding, well, forget about the probability. If I know where one particle is at a given position, given that there is a size of this particle so that they cannot overlap, there is an excluded volume interaction over here, this question becomes even more complicated. So with this thing, if I now go to an n particle system where n is of the order of 10 to the power 23, the Avogadro number, our problem is even more complicated. So we cannot have the deterministic picture that we had when we started off with one particle. We can make an effort in solving this problem, but three particle becomes even more complicated, right? So we can make an effort in solving the two particle problem, by going to the center of mass frame and figuring it out, but 3-particle problem becomes even more complicated analytically. And the whole real picture when you have n particles in the system is even more complicated. So what do? We essentially sacrifice this deterministic. We have too much information in our hand, and we essentially sacrifice this deterministic picture that we know from classical mechanics to go into a probabilistic picture. Now the state for an n particle system, or for any particle system, so n can be 1, 2, 3, anything, the state of the system is characterized by the coordinates and the momenta, right? So for this, there are 6n degrees of freedom. So you have 3n translational degrees. Well, sorry. Let's write coordinates. And you have 3n momenta. We are ignoring the internal degrees of freedom over here. So there are 6n degrees of freedom altogether. Since we have 6n degrees of freedom, 3n coordinates and momenta, one can try to visualize the phase space of this system. It's complicated to visualize, but one can think about the phase space of the system, a 6n dimensional space where this particular quantity, the state qi, pi, is represented by a point, right? So therefore, in the phase space, there is a point. This is a point. We shall denote it by this vector x capital N, where x capital N is equivalent to q1, q2, all the way up to qn, and then p1, p2, all the way up to pn, right? So given in the phase space, there's this at any instant of time, if you had the knowledge, or if you had the tools to know all the coordinates and all the momenta of this particle, of this system, then essentially you can plot it in the 6n dimensional phase space, and this will just be a point. But then you can measure, if you are able to measure, then you can track this state of the system. You can track the coordinates and the momenta for later times also. Therefore, you see that in the phase space, the time evolution, so the movement of the particles within this box essentially is going to give you a trajectory in the phase space. However, one has to realize that since this contains so much of information, that this deterministic picture of keeping track of all the coordinates and the momenta starting from the initial conditions at all later times is just an impossible task. So what we say? We rather say that, look, we are going to sacrifice this, and we are going to talk about a probabilistic description of this evolution of the system, time evolution of the system. So what we say? We say that in the phase space, the state of we can only know with certain probability the state of the system. We cannot exactly for sure know with certainty the state of the system. We could have known that if we could have solved the Newton's equation of motion, written down the equations of motion, used the initial conditions and solved it. But this is just an impossible task for an n particle system where n is of the order of 10 to the power 23, right? So therefore, one can think about the phase space as filled with a probability fluid. And our task is to figure out what this probability density is going to be, or how the evolution of this probability density is going to be, right? So how the rho of xn comma t is going to evolve. What is the dynamical equation that governs the evolution of this probability density? Note that this probability density rho of xn comma t is essentially an n particle probability density, right? It depends on all the coordinate and the momenta of all the particles. However, in reality, in practice, we do not, so this contains too much of information that we need, but we do not need so much of information. The main purpose of this density is typically to calculate expectation values or correlation functions which are typically measured in the experiments. And therefore, so we at most need generally one body or two body probability densities, right? If you recall, then this is what is called a, in terms of probability, in the probability theory, this is what is called a joint probability distribution. And from this joint probability distribution, we can construct one body or two body probability densities, which are reduced probability densities. Now, typically, let's just write this. Typically, this rho of xn comma t is an extremely complicated quantity, and it's not trivial to evaluate this. So essentially, one breaks down this problem into one body or two body probability densities. So there are hierarchy of probability densities that you have: one particle density, two particle density, three particle densities, so on and so forth. So you take this equation, dynamical equation for rho of xn comma t, and then you essentially break it down into several dynamical equations that involve one particle, two particle, three particle, such reduced probability densities. And then these probability densities are essentially, they form an equation which is called BBGK hierarchy, right? Bogoliver, Born, Green, Kirkwood and Ivan hierarchy. So in systems, depending on the system you are looking at, sometimes it is possible to close this hierarchy and to estimate this one particle and two particle densities exactly. But typically, it is not possible for in evaluating this quantity exactly in a classical system, right? So now what we want to try to do is we want to figure out how to measure, how to write a dynamical equation for this. Since I have an n particle system that obeys Hamiltonian dynamics, that means that Pi dot is minus del Hn del Qi, and Qi dot is plus del Hn del Pi. Further, I also have the Hamiltonian of the system as a constant. This follows from the conservation of energy. So from this particular equation, it is clear that in the phase space, if I construct this vector xn, then this vector xn is going to trace out. So this is just a schematic interpretation. In the 6n dimensional phase space, if I construct this vector xn, then the tip of this vector essentially traces out the surface which is given by h of xn is equal to E, right? If I had the capability of solving this n particle system, solving these equations of motion exactly for all the particles, then I know that I will trace out a trajectory in the phase space, right? But this trajectory by its property is not going to intersect with itself. But this uniqueness is lost because of my inability to keep track of so much of information. So for example, if I have this n particle system, I can start off, the initial conditions might not be known exactly for us. So if I start off with xn0, precisely with xn0, and then I track xn as a function of t, solving the Hamilton's equation of motion, then this is the picture that I expect. I expect that a trajectory is going to form in the phase space, which is not going to intersect with each other. But it can happen, it will very well happen that I may not know the initial condition of all the particles. So there is an uncertainty which is associated with this initial condition, and therefore there is also an uncertainty which is associated with the subsequent trajectories, right? So essentially you get a bunch of a spread in the phase space, right? So if you wait long enough, then this phase space will be completely filled by these trajectories. We'll come back to this point. This is one of the pillars of statistical mechanics, what we call ergodic theorem. However, right now, so there, what we want to emphasize, as we have done earlier, is that we want to imagine or think of this phase space to be filled with a continuum of state points. And since I have a continuum of state points like a fluid, we have defined this rho of xnt, so that the probability, if you want to say that what is the probability of finding the system within a region R, then that probability is rho of xn comma t dxn integrated over R, right? Where dxn, the measure is dqi dpi. On the surface. So you also need to include delta of h of xn minus e, right? Nevertheless, so we will see that we can circumvent this delta function only in the thermodynamic limits, but that we will do it later on. So of course, rho of xn comma t dxn, if you allow all values of energy that starts from 0 less than equal to E, then this is going to be normalized, this is going to be 1. And as we said, that the probability of finding the system in a region is rho of xn comma t d of xn. So now I want to evaluate the flow of probability from this region R. Consider a volume V0. Oops. Right? Then the probability of finding the system within this volume is P of V0 is equal to integration over V0 rho of xn comma t d of xn, right? Now, if I have this region V0, so let's not make it a sphere, let's make it slightly arbitrary, so if I have this volume V0, this will enclose a surface S0. So the time derivative of this probability, if I want to write down del t of P of V0, is going to be del t of rho xn comma t d of xn V0. This rate of change of probability will be entirely due to the probability which is flowing out, right? If you denote V, this V, which is essentially xn dot as the velocity of the state points, then just as you have probably done in fluid mechanics, if you have not done, then this is how you do it. Then this is integral over surface rho xn comma t. We will say xn dot over here, right? So this is how you write down. This equation that you see over here is essentially it's one of the forms of, it's the continuity equation. So the change in the density, in the probability density within this region V0 is entirely due to the probability which is flowing out of the region through the surface that is enclosed by V0, and that is the left hand side, right? So it follows, therefore, integral d of xn del rho del t plus, if I use the divergence thing, convert this surface integral into a divergent into a volume integral using the divergence, then this becomes divergence of x n rho of xn comma t times xn dot is equal to 0. Since this is valid for any arbitrary volume V0, this means that the bracketed quantity that you see over here must be 0, so that we have a dynamical equation for evolution of the probability density, which we write down as x dot n is equal to 0. This is just a balance of probability. It's the continuity equation that you are writing down for the probability density rho of xl, right? Let's write down this equation explicitly. What does this mean? This means that I will expand this divergence term. I will write del rho del qi rho qi dot plus del pi rho pi dot. I have suppressed rho xn. This means rho in this equation, right? So there's a sum over this. Let's see. Let's do this sum over I qi dot del rho del qi plus rho del qi dot del qi plus rho del pi dot del pi plus pi dot del rho del pi must be 0. Let's collect the terms together. Sum over I want to put this term and this term together, so I have qi dot. You will see in a moment why I want to do that. Sorry, this is del qi plus pi dot del rho del pi plus sum over I rho del qi del qi dot del qi plus rho del pi dot del pi is equal to 0. Now recall your Hamilton's equation of motion, which says that pi dot was minus del hn del qi, and therefore okay, let's write down the second equation. Qi dot was del hn del pi. So this means that del pi dot del pi is equal to minus del of hn del pi. It gives you a mixed derivative, and similarly del qi dot del qi is going to give you del of hn del qi del pi. Since hn is essentially analytic, therefore it follows that these two mixed derivatives have the opposite sign. They are equal. The mixed derivatives are equal. Therefore these two terms, del pi dot del pi and del qi dot del qi, will have opposite sign, so that this term vanishes, and therefore you have an equation which is del rho del t. I will take it to the other side. Sum over I. Let us replace this del hn del pi del qi plus sorry, it has to be minus del del qy hn qy del del pi times rho. We call this as an operator now, which is n. The superscript n essentially denotes that it's an n particle operator, so this equation becomes hn times rho. So I have del rho del t is equal to minus of hn rho. This is an n particle differential operator. Typically, this equation is recast and written as L hat n times rho, where L hat n is minus I h hat n. And this operator is called Liouville operator, right? So, this, if you look at it carefully, you can easily do it, that this is a Hermitian differential operator. I leave it to you as an exercise to prove that this is indeed a Hermitian operator. It's not very difficult to do. The solution to this operator is I want to write down the solution to this differential equation, so that rho of xn t is e to the power minus I L hat n t rho of xn comma 0. So given the initial probability density, I can know the probability density at later times by operating this differential operator, this quantity e to the power minus I L hat n on the initial probability density. If, let's say, del rho del t is equal to 0, right, which means that you have actually no longer have this density, probability density, rho of xn of t becomes just a function of the phase space variables and no longer is a function of time. Typically that is what happens when you are in equilibrium. Then essentially that means that ln of rho xn is equal to 0, which means that del hn del pi, del rho del qy minus del hn del qy del rho del pi is equal to 0. This can only happen when rho is a function of hn, which is equivalently like saying that rho is a function of the density. If that is the case, then you can see that del rho del qy is del rho del hn del hn del qy, and del rho del pi is del rho del hn del hn del pi, right? And when you substitute these over here, you will see that this is going to give you 0. So very important thing, that for a n particle system which obeys Hamiltonian dynamics, the equilibrium probability density rho of E of xn must be a function of the energy, right?